So this is for Module 9. I put the slides up in the announcement section, so you should download it and so you can follow along. For the first few slides, it's just a background information. So I'm going to start with slide 10. So we're talking about the salesman problem. So there are a few words you got to know. So the tour. So the trip is that it starts from one area, one site, and then you go back to the original site, and you just visit each site once. And it's optimal when it has the least cost, so like the shortest distance or lowest cost, and such and such. So if you minimize the total cost of the tour, it's called a traveling salesman problem. So some more background information. Okay. And so when the gist of this module is modeling a TSP, and we're going to be talking about the Hamilton circuit and the Hamilton path. So the deal is, it's in the graph, it's the optimal tour if the Hamilton circuit has the least total weight. Okay, so that's what we're going to be talking about right now. So just a summary of a TSP. So the sites will be considered vertices on the graph. The cost will be the weight of the edges. The tour we'll be talking about the Hamilton circuit. And if it's optimal tour, that means it's a circuit of least total cost. Okay, so moving on. So we talked about Euler circuits and Euler paths in modules 7 and 8, and so the kind of equivalent to that is the Hamilton paths and the Hamilton circuits. The difference is that for the Euler circuits and path, the name of the game was to find the paths or circuits that include every edge, but then you touch every edge once and then only once. With the Hamilton paths and the circuits, the difference is that you touch every vertex once and then only once. So if the paths or circuits have that property, then they're called the Hamilton paths and the Hamilton circuits. So then last time we touched every edge once. Now we're touching the vertex once. Okay. So here's a summary. Okay. So here's the difference between Hamilton and versus Euler. If you remember, this has a Euler circuit, and we know that because from one of the theorems, it says the vertices are all even, so that makes this graph a circuit. It also has a Hamilton circuit. For example, if this is what you have to do in your assignment, right here. Here's how you do it. So for example, let's start with A. You just have to do a trial and error, but for this answer, you go A, F, B, C, G, D, E, and back to A. So I kind of went around, but then we only touched each vertex once, and then returned to A. So there are many other ones. So that's the kind of similar thing you have to do for your assignment here. The clue is you can start with so there are 3 ways to do this. One is you start with the A. The other one is you start with the C. And I'll leave it up to you to figure out the last one, but you just you have to find 3 paths or 3 circuits given this graph here. Okay. So some more difference between Hamilton and Euler. A few more examples. So this one has a Hamilton path, but no circuit. And it does not have an Euler circuit, but it does have Euler path. So I have you read this to figure out what am I talking about here. So no Euler circuit, but it does have Euler path. no Hamilton circuit, but it does have a Hamilton path. So that's the kind of thing you'll be looking at for the next couple of slides. Okay. In this section from slide 19 to 26, so here's a summary. It will help you with assignment problem number 5. Okay. More difference between Euler and Hamilton. Okay. One other thing that's not covered in the lecture notes is the concept of a complete graph. Say at a graph, it has no loops or multiple edges, but then all the vertices are completely interconnected, meaning that every vertex is connected with each other, so to every other vertex. Then that graph is called a complete graph. And we need to denote that by the symbol Kn, K being the complete graph, N being the number of vertices. So let's say, so I'm going to show you example of K5. So that's a complete graph with 5 vertices. Here we go. So all the vertices are connected with each other, and there are five of them, A, B, C, D, E. So this is an example of K5. Okay. In your assignment, you'll be asked to figure out different properties of a complete graph. And to do so, here are the properties of a complete graph. So those are the questions that could be asked from a complete graph. One is the degree of every vertex. The next one is the number of edges in any complete graph. The third one is number of Hamilton paths in any given complete graph. And the other one is, the last one is the number of Hamilton circuits in complete graph. So the formula for first one, the degree of every vertex, it's n-1. You can see the other 3. This explanation point, it's called a factorial, so an n factorial. The way it happens is that if you have 5 factorial, for example, you multiply that number and then 1 less than that until you reach 1. So 5 factorial will look like this: 5, 4, 3, 2, 1, or 1, 2, 3, 4, 5. You can do this in your calculator as well, punching 5 and then this factorial character. And you should look that up on how to do that in your calculator by looking up factorial. It should tell you how to do that. If you cannot figure out how to do that, just do manually 5, 4, 3, 2, 1. And then if it's a circuit of a complete graph of K5, then you have number of Hamilton paths will be 120. And then the number of Hamilton circuits will be 5 minus 1, so it will be 4 factorial. Answer to that question would be 24, as shown on the slide here. Okay, so that covers all the questions from Module 9 assignment. If you have any questions, let me know, and I'll help you out with a reply.